Hello everyone. In the previous session, we have seen the summary of all the different logical group of instructions. So I believe it's about time we should concrete all the concepts that we have gathered so far. So welcome to the session, Logical Instructions, Solve Problem 1. Without any further ado, let's get to learning. Coming to the topic that we are going to cover in this session, today we are going to solve a problem on logical group of instructions. So let's begin. Consider the question. Write an 8085 assembly language program that takes data from memory location X, sets the MS2 bits to 1. Now here, MS stands for most significant. So we are talking about setting the most significant 2 bits to 1. Complements the 4 bits in the middle of the byte. So after the most significant 2 bits are set to 1, thereafter we are supposed to complement the next 4 bits which are in the middle of the byte. Resets the LS 2 bits to 0. As you have already presumed, here LS stands for least significant 2 bits. So we are supposed to reset the least significant 2 bits to 0. And finally, we are supposed to store the result at the memory location Y. Now, if you notice, at the very beginning of this chapter, I told you, before writing any program for 8085 microprocessor, we need to learn about all the different group of instructions in details. But let me prove my claim wrong. We can also write down programs with the knowledge that we have gathered so far. So let's try to solve it. Now, before we dive straight into writing down the program, let me explain how the solution is to be found. If you notice, in the question it has been mentioned that we are supposed to write an 8085 assembly language program that will take data from the memory location X. Now, X can be any memory location within the memory which is associated to 8085 microprocessor. Now, if we talk about the memory, we already know within the memory locations, we can only store 8 bits. And that's pretty evident because in the question also, the term byte has been mentioned. Now we already know a byte is comprised of 8 bits. And we are supposed to take that byte from the memory location X. Now where will it be placed? We know we can place the data from the memory location into the accumulator. And the accumulator is also of 8 bits. Therefore, let's say we are going to name the 8 bits like this. As you can notice, the least significant bit we are notifying as B0, whereas the most significant bit is B7. Now notice the question. At first, we are supposed to set the most significant 2 bits to 1. And how to do that? If you remember, when we were learning about the basics of OR operation, we derived these two logics. Using the second logic, we can selectively set the bits of the accumulator. And that was X or 1 is going to give us 1. Now in the question it is mentioned, we are supposed to set the most significant 2 bits to 1. So for the most significant 2 bits, that is B7 and B6, we will use this logic. And for now, for the remaining bits, since we don't want to alter them right away, we are going to use this logic, that is X or 0 is going to give us X, which is going to help us keep these 6 bits intact. So this is going to be our first operand, and we are going to perform OR between this operand 1. Now coming to the operand 2, we are going to choose that operand carefully. Since we want to set the most significant 2 bits to 1, so for these 2 bits, we will have 1s. And as I told you earlier, we don't want to alter these 6 bits, so for them, we will have 6 zeros in the second operand. Now once the OR operation is performed, can you guess what will be the result? Well, it is going to be 1, 1 followed by the bits B5 to B0. Notice the most significant 2 bits have been set to 1. Coming to the rest of the bits, they are still intact. Now this is the outcome that we want after we perform the OR operation. The first operand is already in the accumulator. This is going to be our second operand. Now can you figure out what will be its value in hexadecimal? In order to find it, all we have to do is group the bits 4 at a time from the least significant bit towards the most significant bit. Now if you consider the first nibble, it is 1100. It is 12 in decimal, and in hexadecimal we call it C. Coming to the least significant nibble, all zeros, which is represented by 0 of hexadecimal. So our second operand is going to be C0H. Now in order to perform this, we will make use of the instruction ORI C0H. Notice, we already have loaded the content of the memory location X inside the accumulator. With that, we are performing OR and we are sending the immediate data C0H within the instruction itself. After the execution of this instruction, the content within the accumulator is going to be this. So the bit sequence 11 followed by B5, B4, B3 till B0 is going to be our new operand. Now notice, once the most significant 2 bits have been set to 1, thereafter we are supposed to complement the 4 bits in the middle of the byte. That is, the bits B5, B4, B3 and B2. Now how to do this? If you recall it, when we learnt about the basics of XOR operation, using this logic, X exclusive OR 1, which gives us the output of X bar, we can selectively complement bits of the accumulator. And we are supposed to perform the complementation, right? And since this is our first operand, which is already residing inside the accumulator, and we are supposed to complement these 4 bits, therefore, in the second operand, we will choose 1111 for the middle of the byte. Now apart from these 4 bits, for the most significant 2 bits as well as the least significant 2 bits, we will choose the bits using this logic. Since we don't want to alter them, we will choose zeros for these places. Now if we perform the exclusive OR operation, the outcome is going to be this bit sequence. Notice, the most significant 2 bits, which were previously set to 1, are intact, and the same can be stated for the least significant 2 bits. These are still B1 and B0. However, the 4 bits in the middle are complements of the previous value. Let's now find out the hexadecimal equivalent of the second operand. If we group them 4 bits at a time, notice 0011, it is 3 in hexadecimal, whereas 1100, 12 of decimal, but C in case of hexadecimal. So our second operand is going to be 3CH. Once we have executed the instruction ORI C0H, thereafter, in order to replicate this operation, we will execute the second instruction XRI 3CH. Notice, we are using the instruction XOR immediate data with accumulator 3CH. For this, the accumulator holds the first operand, that is this bit sequence, and we are sending the second operand via the instruction itself. Now once this instruction following the ORI C0H instruction has been executed, within the accumulator we will have the bit sequence 11, thereafter the complement of the 4 bits of the middle, and till now the least significant 2 bits are intact. Now we are supposed to reset the least significant 2 bits to 0. If you remember, using the AND operation, we can selectively reset the bits in the accumulator. For this, we will have to make use of this logic. X and 0 is going to reset the content of X. Now, if you notice, we only want to reset the least significant 2 bits, B1 and B0. The rest of the bits, we want them to be intact. So with the first operand, we are going to perform AND, but the second operand is going to be chosen using these two logics. Since apart from the least significant 2 bits, we want to keep the rest of the most significant 6 bits intact, in the second operand, the least significant 2 bits will be zeros and the rest of the 6 bits will be ones. So once the AND operation has been performed, what is going to be the outcome? Well, in the outcome, the most significant 6 bits will be intact. That is, the most significant 2 bits will be set to 1. The 4 bits in the middle will be kept as the complements of the previous 4 bits. However, the least significant 2 bits will now be reset to zeros. Can you find out the hexadecimal equivalent of the second operand? All we have to do is group them, right? Now all ones or 4 ones is 15 of decimal, which in hexadecimal is F. Coming to the next nibble, 1100, 12 of decimal, or in hexadecimal C. So our second operand is going to be FCH. Therefore, once these two instructions have been executed, thereafter in order to replicate this entire operation, we will use the instruction ANI FCH. Here also, we are using AND immediate and we are sending the immediate data FCH in the instruction itself. So this is going to be our sequence of instructions. Now let's begin writing the program. First of all, let me tell you, for the programs of 8085, we need the assembler. And the reason for that is, the 8085 programs are known as assembly language programs. All these instructions that we are writing, these are called assembler directives. Or in other words, the instructions which direct the assembler to perform some tasks. Assemblers are also language translators, but they are not the high-level language to machine code translators. Rather, they translate assembly language programs, which are also known as the mid-level programs, into the machine codes. Now, before we perform these operations, we are supposed to load the data from the memory location into the accumulator. And for that, we need to use the data transfer instruction LDAX. I hope you remember the mnemonic LDA stands for load the accumulator and X is a memory location, so the accumulator will be loaded with the content inside the memory location X. Now once we have loaded the data inside the accumulator, now we can perform these sequences of instructions. So at first, we will execute the instruction ORIC0H. I hope you remember what it will do. It is going to set the most significant 2 bits to 1. Now we need to complement the 4 bits in the middle of the byte. For this, we are going to make use of the second instruction, that is XRI3CH. Then we have to reset the least significant 2 bits to 0, and that will be done using the third instruction, which is ANI FCH. Now notice, after all these 3 operations, the updated data is still inside the accumulator. And in the question it is mentioned that we are supposed to store that value inside the memory location Y. For this, we will use the data transfer instruction STAY. That is, store the contents of the accumulator into the memory location Y. Are we done? Not really. We also need to specify the assembler that this is the point after which we are supposed to halt. So we need the instruction HLT to let the assembler know when to stop the execution. Now in the question, the memory locations have been mentioned as X and Y. And we already know the memory associated to the 8085 microprocessor. In that, we have got 16-bit addresses. Suppose in the memory location 3300, we will have the input data. So X, let's suppose it is going to be 3300. And once the entire operation has been done, say we are going to store the result in the location 3310. So in the actual program, we will replace Y using the address 3310. Now let's talk about the data. We are supposed to set the most significant 2 bits to 1, complement the 4 bits in the middle of the byte, then we are supposed to reset the least significant 2 bits to 0. How about we choose the input data which can demonstrate all of these in a beautiful manner. Say we are going to choose these 8 bits for input. Notice, the most significant 2 bits in here are zeros, which are supposed to be set to 1 after the program has been executed. Coming to the 4 bits in the middle, these are currently 1010. We are supposed to complement these 4 bits, and we have designed our program in such a way that is, after the execution, these 4 bits will become 0101. Finally, the least significant bits are 11, which are supposed to be reset to zeros after the execution. Therefore, if our program is correct, by the end of the execution, at the memory location 3310, we are supposed to get this result. Now, can you tell me the hexadecimal equivalence of the input sequence as well as the output sequence? Notice, 0010 is 2, where 1011, that is 11 of decimal, in hexadecimal it is B. So 2B is going to be our input data. Now coming to the output bit sequence, 1101 is 13, which in hexadecimal is D, and 0100 is 4 in hexadecimal. So in the memory location 3310, if we load the data 2B after the successful execution of the program, at the memory location 3310, we will have the result D4. Now this entire thing is conceptual. Let me now show you whether we will get this data in practical mode. Now in this course of microprocessor and microcontrollers, we are going to use this online emulator called SIM8085. You too can use this in order to execute the assembly language programs using this website www.sim8085.com. Now before we write down our program and execute it, let me walk you through the various components of this emulator. By the way, I'm referring to this as emulator, so let me tell you what's an emulator. Emulators usually help in modeling old hardware and software by recreating them using modern technology. As you can see, this emulator, that is SIM8085, this has been created using these web development tools. Now this is the code editor where we are going to write down our code. As you can see, the name of the tab is main.asm. Now .asm is the extension for assembly language programs. So this is the code editor where we are going to write down our program codes. Now to the top left of it, as you can see, all the registers have been specified. These are also specified in groups. That is, at first we have the accumulator, and PSW is specifying the flags register, which is also known as processor status word. Then we have got the BC register pair, then D register pair, thereafter HL. Then we have the stack pointer and program counter. Now if you notice carefully, as the prefixes, we have got 0x in all of them. And I hope you remember that 0x prefix is used for hexadecimal. So clearly, we will deal in hexadecimal digits. Now if you come to the very first pair, here, the first part of the pair is editable. If you double click on it, you can edit the content of the accumulator. But remember, the content of the program status word or the flags register is not editable. Now in case of BC, as you can see, after 0x, we have got 4 more digits, and if we want to edit it, we can edit all these 4 bits. Now suppose you want to load the data only inside the B register, so just edit the first 2 digits. If you wish to load some data inside the C register, then just edit the remaining 2 digits. The same can be stated for DE as well as HL. However, the contents of the stack pointer and the program counter are fixed. You cannot edit them. Now to the bottom left corner, you can also notice the flags. If I check the carry flag, this will mean the carry flag has been set. Unchecking it will reset the carry flag. Now on the right hand side, you can see the memory view. We already know, in case of 8085, the associated memory has 64K, or to be precise, 65,536 memory locations. If you notice, in this memory view, the memory has been shown in a grid view. The starting address here is 0000. So the most significant 3 digits of hexadecimal is the row heading, and the least significant digit is the column heading. Now in this particular grid view, as you can see, we have got the addresses starting from 4 zeros till, if you scroll this, you will find the last address of this grid view, that is 10F. Now in case of any of the memory location, if you go to that particular location, as you can notice, this location is 1048. Now double clicking on this location, this will become editable, and we can enter any value in that. And if you notice, these are 2 hexadecimal digits, which in binary is 8 bits. Now notice, if we scroll it back, and then from the list, go to the last item, and then scroll it again to the forward, this is the last location. And what's the location? F. So within the memory, this is the last location. So we can access anywhere in the memory using this drop-down list and the grid view. Now notice, at the top of the main tab, we have got a few buttons. Let me explain what these do. At first, we have got this button, which will assemble and load the program. And by default, in this emulator, the programs are going to be loaded from the memory location 0x0800. So this is going to be the starting address of the memory location from where the programs will be loaded. The next button will help us run the program, and clicking this button will run the entire program at once. We can also run the program in step-by-step mode. Using this button, we can run one instruction at a time. Coming to the next button, clicking on this will stop the program execution, and we will be able to return to the editing mode. Finally, this button is going to reset everything that we have just edited. So this was the brief walkthrough of this emulator. If you want to know about it in details, you can always go to the help section where the creator of this emulator has embedded one tutorial. Anyway, let's now get back to our program. Now this was our program. As you can see, we are supposed to load the accumulator from the data which we will update at the memory location 3300H. We can find the memory location from this drop-down list. We have the location in here 3300. Now this is the location 3300. If you remember, we are supposed to load the value 2B to this particular location. So let's edit this. We are supposed to load 2B, right? Now since we have specified the input data inside the memory location 330H, let's now go ahead and assemble and load the program. Once it is done, we will receive this prompt. It shows that our code has been compiled and has been loaded from this particular memory location. Now using this, we can also go to the memory location directly. Would you like to see the hex codes for the respective instructions? We can do that. All we have to do is input the memory location 0800. Notice the hex code for LDA is 3A, right? Then we have 00, that is the lower order address, and thereafter 33, that is the higher order address. Then the hex code for ORI, F6, and thereafter C0, the immediate data which we were sending. And like this, till the memory location 080C, we have got all the instructions hex codes. And you already know 76 is the opcode or hex code for the halt instruction. Anyway, we are supposed to get our result at the location 3310. So let's go to the grid view of 3300. We have to scroll it back. Notice, we gave our input data inside the location 3300, which was 2B. Now the program has been assembled and loaded. All we have to do is execute it. So let's do that. Notice, in the memory location 3310, we have got the value D4. And this was the value that we were supposed to get, right? And if you notice another thing, we stored the accumulator's content into this location. So within the accumulator also, we have got the value D4. So this is how we can use this emulator SIM8085 to run our programs. So in this session, we covered the topic, the solve problem on logical instructions. We actually wrote our first program in 8085 microprocessor. Alright people, that will be all for this session. In the next session, we are going to solve another problem on 8085 microprocessor's logical group of instructions. So I hope to see you in the next one. Thank you all for watching.